Okay, so today's video is going to be very interesting as I'm going to be talking about Bose-Einstein Einstein Condensate. Okay, condensate. So let's start with basics. We know that how many states of matter are there? There are one, two, three. Some people will say three, but there's actually fourth one as well, and many more. But the most common, I'm talking about the most common: solid, liquid, and gas. But the fourth newest one is plasma. Yes, plasma is also one of the states of matter. First of all, okay, before we talk about states of matter, we will talk about what is matter. Because matter, when we till we don't describe matter, we can't go on. So matter is something which has mass and it it occupies space, okay, or volume, occupies volume, okay. So then here we have something which has mass. I just want the key points. Something which has mass and occupies volume. And what are they? Solid, liquid, gas, and plasma. Okay, I'll just talk about uh, solid. No, solid. Okay, I'll just talk about the shapes, the like how it is in the arrangement in each matter. Number one, solid. In solid, they arranged in arrangement. The arrangement is proper. I will not say there is no gap. There is gap, but too small. Too small. Then we have number two, liquid. We have again not that much distance, but still there is some uh, force. Here, wait, let me cite more force. Here, uh, less force. I'll tell you why I used less here, but not in for gas. So, okay. Then when we talk about liquid, sorry, not liquid, gas. Gas, most of the people says that, wait, no, this is way too most of the people will say that right now there's no force between them and they're free to move. No, there is force. There is force. Never say there's no force. There is force, but is too less to attract them to each other. There is a force. Never say there is no force. There is always a force between matter. Then comes the fourth state of matter, plasma. Plasma is, okay, we know that gas is the distance. This distance a lot. But plasma is, uh, yeah. So, yeah. Wait, before we talk about plasma, we'll talk about Bose-Einstein Condensate. To sum up, Bose-Einstein condensate, conden, condensate, condensate. Okay. So what is Bose-Einstein condensate? We didn't write Einstein. Einstein condensate. This is done at, okay, well, let me write a key point. Done at lower level, lower temperature. And now by lower temperature, I don't mean by the temperature which is in like fridge, which is less like uh, the normal temperature of fridge. I'm talking about low means near absolute zero, near absolute zero. Okay. Okay, then one more point, that we'll then talk about the points as well, no way. Then we will have the energy of the particles or elements. Then, okay, so on, but let's talk about how it is. Let's suppose I have this atom, okay, and I want to decrease its temperature, its temperature. What could I do? Okay, what could I do? I want to decrease its temperature. I have some people. It's mostly it's like the answers would be to keep it somewhere cold or keep it in an isolated place. But the experiments this done is using lasers. You can actually cool the cool particles using lasers. How? I'll show you. Let's suppose we have a particle over here. Okay, so when we have a laser coming towards it, this is a monochromatic laser. That's what laser is, right? One frequency laser. So when laser is coming towards it, the energy of that, wait, let me change color. This one. Energy of that laser or that photon will be absorbed by this particle, and then its velocity will decrease and will stop for a moment. Okay, it will stop for a moment. Then what will happen? It will then give out that photon again, emit, absorb. Okay, so this is one reason. So how can we do it? What we will do is that how, okay, enhancement. I'll just say enhancement. Okay, how we can enhance it. Okay, particle. Now instead of laser from one direction, I will be giving pairs. I'll be making pairs of lasers from all the directions. Okay, like one here, second here, third here. So they're pairs and they're attacking or they're hitting the particle from all sides. And what's happening is that the energy of particle is decreasing. Okay, decreasing. And since this is a photon over here, like over here this is a photon, when that particle is stationary, that this photon will be of red color, longer wavelength, and P equal h over lambda. Right now it has more momentum because it has velocity. Okay, This has more velocity, this has more momentum as it has velocity. So what we want the momentum to decrease. So what will happen is that when we give it for a wavelength, it will absorb it, and it will constantly it will absorb, and what will happen is that its energy will decrease. E is equals to, energy will increase or decrease, h lem, or let me say, uh, energy will decrease. We are actually giving it energy, so it will increase. Wavelength will decrease, and that's what we want. We want the particles momentum with this, they are correlated, they are combined. What will happen is that the momentum of the particle will decrease, or no, increase. It will stop, it will come to a stop. The wavelength decrease. The what I mean by that is the vibration will be less. There will be less vibration, and they will come to a stop if I'm seeing multiple particles, if there are, okay. So their vibration will come to a stop, and after a while what will happen is that they will reach, the particle will decrease, the momentum of the particle will decrease, and they will reach a point where where the wavelength of the particles are now 1. They're the same, okay. And how I would say is that if this is energy level, okay, and the electrons are jumping here and here and here, up, sorry, wait, let me use a different color, up, down, down, up, whatever, so on. So when this happens, what happens that now if I draw the energy level, all the electrons will be at same point. Oh, sorry, this is what it will have, okay. So here one phenomena of quantum mechanics comes in, and this is related to quantum mechanics. This is something known as quantum navigation, okay. This is part of quantum navigation, okay. So now this whole field, even though it's made of different particle, of different particles, but have same property. Right now at this point they are wave and particle. How? Okay, let's suppose I want to look at this particle, okay. I have a magnifying glass, magnifying glass, okay. So if I look at this particle with magnifying glass, what will happen? What I will see is that even though they are made of particles, I will see mist. I'll see that they are one. I will only see clouds. Sorry, what's happened? Seen as one entity, okay. So This is what Bose-Einstein condensate is, that you decrease the temperature of the particle so much that the wavelength is becomes one, and they are now in a state that affecting that state will affect the whole system, not only one particle, whole system together. So we can also, here again one more concept comes in of quantum mechanics, quantum entanglement. Now we can say that, right? Because we can say, okay, how we can say that is that we just talked about that it being one entity, right? So that means we can say that, okay. So why? Because they are now one entity and affecting one will affect the whole system. That's what quantum mechanics is, affecting quantum entanglement. If this is spin up, this will be spin down, spin, spin. Okay. So what is happening here is that the main goal, okay, one more thing over here when we're talking about what was it, how when we were cooling the atom to its to absolute zero, near absolute zero, and it's actually the values 273.150 Celsius. Okay, so then we have something as Doppler effect. Doppler effect you have heard of? Then this is Doppler cooling. Okay, Doppler cooling. What we do is that what actually happens to make the Bose-Einstein condensate. Okay, so I will be talking about the, here we'll talk about Doppler effect. Okay, so Doppler cooling, Doppler effect. First of all, what is Doppler effect? Doppler effect. Okay, what is Doppler effect? When an ambulance, okay, and is traveling in this direction and it has a siren, what will that siren do? It will make a wave, it will make a sound. This is how the sound will be. This is a person. If it's stationary, the wavelength, here again wavelength will come in. Wavelength is same in all direction. Okay, but now We can see the effect here. Look. The wavelength is more in the direction of movement. When this object, let me write, when this object moved in the direction of the person, the wavelength increased. Okay, so this is what Doppler effect is. So that's the same as Doppler cooling. Here, when the particle is moving towards the wavelength, the energy of light, laser, what happens that the wavelength of this particle is decreasing because it's opposing, it's going towards it, and this helps the particles to decrease. If you can understand, if you understand Doppler effect, this is what Doppler cooling is the same as it. Decrease in cool or temperature. Okay. So yeah. So then to summarize, or is there something I missed? No, I talked about everything. Yeah, Bose-Einstein. So I have shown how Bose-Einstein is made. Bose-Einstein condensate is made. And okay, one more thing. At this point, if this is the wavelength of multiple, wait, let me highlight. Wavelength or psi of, not wavelength, psi of individual particles, or one more thing, particle. Here we have the particle boson because of it having integer spin. That's why it was used, as others have half or half spins, yes, like electron. So wavelength of individual particles. Now this wavelength of Bose-Einstein condensate. Okay. One and one psi. When I open the psi, then again it's a huge another topic to discuss about, which I have already done. Psi of x and 1 plus psi of more 2 x and 3. This is, and so on. Thank you.